this is our AP Chemistry Chapter 10 lesson video, and this is part 4, and so we are finally going to finish up with section 10.8 and 10.9. Alright, so we're going to talk about effusion and diffusion. We talked about those in honors if you took that. But first we're going to continue on with our RMS speed, our root mean square speed that we started talking about on our last video. Okay, so our formula is U equals, and this is supposed to be a giant square root. Okay, so I just kind of put it in parentheses and put square root, or you could raise it to the half. But it's 3 times R times T divided by our molar mass. So R is 8.31 kilograms times meters squared per second squared times mole times Kelvin. So a lot of stuff happening here. Okay, so notice which R value we're using. We're not using the 0.0821. Alright, since molar mass, or M, appears in the denominator, the less massive the gas molecules, the higher the RMS speed. Okay, which makes sense. The lighter the molecule, the faster it can move. Okay, and so again, you can see down here, like oxygen's right here, O2. Alright, we have H2O right here, but helium is over here, and hydrogen's over here. So those lighter gases, they have higher speeds that they travel. Alright, so it says calculate RMS speed, or U, of an N2 molecule at 25 degrees Celsius. Alright, so I know it's N2, so I can figure out my molar mass. So N2, of course, is just 28 grams per mole. I know my R value is 8.31, and I know my temperature is 25, which of course I need to add 273, and so that becomes 298 Kelvin. So I know that my U equals square root of 3RT over molar mass. So then I just plug in. So I do 3 times R, which is 8.31 this time. Okay, well, I guess I can write all those units. I don't normally write all those units like when I'm doing this by myself. But I'll write it this one time. If we have any more of these, I'll probably leave all the units. It's excessive amount of units. All right, times my temperature, which is 298 Kelvin, over my molar mass, which I decided was, oh, whoops, sorry, we got to fix this unit real quick. So when we do molar mass in class, we normally do grams per mole. But if you look, that's not going to cancel out because it's got to be kilograms, because that's what our unit is in our R value. So I almost forgot to change that. Okay, so our molar mass for this one, once I change it, is of course going to be 0.028. So the way we go from grams to kilograms is you just move your decimal 1, 2, 3 places to the left. So that will make it kilograms per mole. Ooh, I almost plugged the wrong number in. Alright, so we get 0.028 kilograms per mole. So that's one thing you do have to be careful of. So it's probably a good thing I did write the units, otherwise I wouldn't even notice. Okay, so see, my kilograms cancel, my moles cancel, my Kelvin canceled. So I'm left with meters squared per second squared. Okay, so once I solve that, I end up getting 515.1. And so I know you're probably tempted to write meters squared per second squared, but remember, we're square rooting the whole thing. So that leaves me with just meters per second, which is an appropriate unit for a speed. Okay, so just be careful. So on this, you've got to make sure your molar mass is kilograms per mole because of the units of R. All right, and don't forget to square root. Some of you just get going real fast and you'll forget to square root. And then don't forget to square root your units too. I will go ahead and tell you, I haven't really seen any questions where you have to calculate this on the AP exam, but hey, just in case you know, I'm going over it. All right, so y'all try this one and then we'll look at it together. So it says, what is the RMS speed? So of course I'm looking for U of helium atoms. So of course I need molar mass of that, which is of course 4 grams per mole. But remember, I need it to be in kilograms per mole, so it's going to be 0.004 kilograms per mole at 25 degrees Celsius. So there's my temperature, but that's going to be 298 Kelvin. So my U is square root of 3RT over my molar mass. So I just do square root of 3 times 8.31 kilograms times meters squared per second squared over moles and Kelvin times my temperature, 298 Kelvin, over my molar mass, which I changed to kilograms per mole, 0.004 kilograms per mole. So my kilograms cancel, mole cancel, Kelvin cancel. So remember, I'm left with meters squared per second squared, but we're square rooting the whole thing. Okay, so on this one, I ended up getting 136, oh, no I didn't, I got 1,362.82, and then meters squared per second squared, square rooted is meters per second. Just like that. So hopefully you got that one right. Okay, so let's move on. Like I said, I haven't really ever seen where they made you calculate that, but just in case. I want to cover everything just in case. Alright, so effusion and diffusion. We talked about these in honors, so let's go back into it. So effusion is the escape of gas particles through a tiny hole into an evacuated space. Diffusion is the spread of one substance throughout a space or throughout a second substance. So this would be an example of diffusion. They open this container and these green particles mix with the blue particles around it. In both cases, gas particles move from high to low concentration. So a lot of people, they think these are opposites. Diffusion is from high to low, so effusion must be low to high. They're both high to low, it's just effusion is specifically when the gas escapes through a tiny hole into an evacuated space. So Grant's law of diffusion and effusion are, and again, I just raised it to the 1/2. I can't figure out how to make a giant square root, you know, whatever. So it's the rate of gas 1 or gas A, like in honors we call this A and B. They just call it 1 and 2 in this book, that's fine. So rate of gas A over rate of gas B is the square root of the molar mass of gas B over the molar mass of gas A. Okay, so notice it's 1 over 2 on this side, but 2 over 1. And so R is just your rate of diffusion or effusion. M is, of course, your molar mass. Gases with lower molar mass will effuse or diffuse faster than a heavier gas because they tend to have a faster RMS speed. Uh-oh, there we go. Is that the next? Oh, my clicker wasn't going to work. All right, so let's look at the first one together. So it says an unknown gas composed of homonuclear diatomic molecules. So homonuclear means it's the same atom, and it's a diatomic molecule. Okay, so that's important. So it's something like Cl2 or Br2 or H2. It effuses at a rate that is only 0.355 times that of O2 at the same temperature. Calculate the molar mass of the unknown gas and identify it. Okay, so y'all, this is important. It says that it effuses at a rate that is 0.355 times that of O2. That means O2 is faster, and this homonuclear gas is slower. So that means this one is going to have the larger molar mass. Okay, so that at least kind of narrows it down for me. Okay, this one has to have a larger molar mass. All right, so we know that our rate of 1 over rate of 2 equals the square root of the molar mass of 2 over the molar mass of 1. Okay, so our unknown only diffuses 0.355 times that of O2. So remember, that means this one's moving slower. So because this one is moving slower, this is going to be my bottom one, our molar mass 1. Now I know you're probably thinking back to honors and you're like, but I thought you said gas 2 is the bigger gas. Well, normally it is, but then that would give us a number greater than 1. So in other words, they've done the gas 1 as the bigger gas. All right, so our rate is the 0.355, and I know you're probably like, wait a minute, but don't I need to plug in 2 numbers? This is the ratio of the rate. It's 0.355 times that of O2, so I don't need to plug in 2 rates, okay? So then my gas, my molar mass of 2 is my 32. Oh, I didn't write it down. So molar mass of O2 is 32 grams per mole, so I'll put that on top. And my homonuclear diatomic molecules, I don't know what that is, so I'm just going to put in X. All right, so then I just solve for X. So of course, just in case you struggle with math a little bit, to solve for X, of course, you'll square both sides first, get X on the top. But once you solve for X, you should end up getting that it is about 253.97 grams per mole. Well, then it says identify. So I calculated the molar mass. This was just coming from me solving from X. If you have trouble solving that for X, then just come see me. You should not have trouble solving for X. All right, and so now we got to identify it. Okay, so we know our diatomics. So we know it's got to be something heavier than O2. So we also have the choice of F2. That's not going to be heavy enough. Cl2 is not going to be heavy enough. Br2 is 80. 80 times 2 is only 160. I2. I2 is 1. So if you look, I2 ends up having a molar mass of about has a molar mass of about 254. Okay, so it ends up being I2 because of that molar mass, because it's 127 for each one, so 127 times 2 is going to give you about that. Okay, so that's what's different in here. In honors, we were always solving for the ratio of the rates, but in here, sometimes you might have to solve for the molar mass. So you just got to be careful, so always pay attention. If it's larger than 1, that means it's moving faster. If it's less than 1, that means it's moving slower. And so in that case, they've made molar mass 1 the larger gas. All right, so y'all try this one. This one's similar to what we did in honors. Okay, so I'll assume you paused it and you tried it. So it says calculate the rate of diffusion rates of N2 and O2 gas. Okay, so for this one, of course, we have rate 1 over rate 2, and of course you can still call this A and B if you like to from honors, is molar mass of 2 over molar mass of 1. Alright, so for this one, N2 is 28 grams per mole, and O2 is 32 grams per mole. And so you know that I like to make gas B the bigger gas. Okay, so this is going to be gas B, or sorry, we'll call it 1 and 2 now. So this is going to be gas 1, and this is going to be gas 2. So my rates equal the square root of 32 grams per mole over 28 grams per mole. So my grams per mole cancel, and I get 1.07. And so that is the ratio. So if you remember in honors, we would then write this sentence, N2 gas F uses 1.0 times faster than O2 gas. But notice here, it just said calculate the ratio. So that is the ratio. So then we're done. All right, so hopefully you kind of remember that from honors. Maybe not the first one. The first one was a little trickier. All right, so let's talk about diffusion and molecular speed. So the diffusion of gases is much slower than molecular speeds because of collisions. So if you look right here, these are moving very quickly, but notice it gets kind of stuck because it's bumping into other things constantly. So the average distance traveled by a particle between collisions is called the mean free path. So, section 10.9, real gases versus ideal gases. So we talked a little bit about this in honors, so hopefully it kind of rings a bell. So real gases do not behave ideally at high pressures and low temperatures because real gases will liquefy or solidify at high pressures and low temperatures. And ideal gas, we assume it's a gas at all temperatures and pressures. Ideal gases are gases at all conditions, while real gases turn into liquids and solids at high pressures and low temperatures. Real gas particles have a volume. Remember, for ideal gases, we assume they don't. And real gases experience attractions and repulsions. For ideal gases, we assume there's no forces between them because they're just very far apart, and they're spread out, and they're moving very fast. So the forces are just very small. But real gases do have those things. Oh, I don't know what that was supposed to be, but we're going to skip over that. All right, so our sample integrative exercise. Oh my gosh, we're almost done. All right, so cyanogen, a highly toxic gas, is composed of 46.2% carbon and 53.8% nitrogen by mass at 25 degrees Celsius and 751 torr. 1.05 grams of cyanogen occupies 0.5 liters. What is the molecular formula of cyanogen? All right, so y'all, I can see that they gave me my percentages, so I can start with that and do some empirical formula here. So I take my 46.2 grams of carbon, and of course I change it to moles, because remember, we're trying to get those subscripts. So I do that, and for this I get 3.85 moles of carbon. All right, and then I take my 53.8 grams of nitrogen, and I convert it to moles. I'm just dividing by molar mass, that's all I'm doing. So I get 3.84 moles of nitrogen. Then I divide by the smallest, which is of course 3.84, which is practically the other number. So I get 1 mole of carbon and 1 mole of nitrogen. So that means my empirical formula is CN. However, they asked me for my molecular formula. Okay, so I can't just stop here. I need to get to molecular formula. So remember, for molecular formula, that means I need to know the molar mass of cyanogen, because then I can divide the molar mass of the molecular formula by empirical formula and figure out the whole number I need to multiply this by. But they weren't very kind. They didn't give us that information. So I see though that they gave me a temperature, they gave me a pressure, they gave me grams, and they gave me a volume. So I can do some calculations here. All right, so what I did first was, of course, I changed my temperature to Kelvin. So this is 298 Kelvin. All right, and then what I did was I went ahead and fixed my pressure to something I can plug into my formula for that ideal gas formula where it had density and molar mass. That's the one that I'm kind of using. All right, so I took my torr, so I took 751 torr, and of course I changed to ATM. You could change to kPa, it doesn't matter. So I got a pressure of 0.99 ATM. All right, and then I used my grams and my volume to get density, because density is mass over volume. Because remember, what we need is molar mass. So we're trying to use this formula right here. Molar mass is density times R times T over P. That's the formula we're trying to use. So I needed density. So it gave me the mass, it's 1.05 grams. It gave me a volume, 0.5 liters. So once I did that, I got a density of 2.1 grams per liter. So now I can plug in. So my density is 2.1 grams per liter. My R value is 0.0821 liters times ATM over moles times Kelvin. My temperature is 298 Kelvin. And my pressure is 0.99 ATM. So if you look, my ATM cancel, my Kelvin cancel, my liters cancel, and I'm left with grams per mole. So once I did that, I got 51.84 grams per mole. So this is my molar mass of my molecular formula. So I add this up real quick and I get about 26 grams per mole. So remember, all we do is our 51.84 divided by our 26, and you're practically going to get 2. So that means I'll multiply this formula by 2. So it becomes C2N2. Whew, that was a long problem for just part A, golly. But it was super awesome though. Alright, so let's move on. We may need information from this one for the other parts, we'll see. If so, I'll just rewrite it on the board for us. So C2N2, all that work just to get that. Alright, so it says predict its molecular structure. So in this case, I just need to draw it. So it's C2N2, so I know C has 4 valence electrons, but multiply it by 2. N has 5 valence electrons, but multiply it by 6 for a total of 10 plus 8, which is 18 valence electrons. Alright, so y'all, we might not have done C2N2 before, but we've done C2H2. So we bond our 2 C's and then give an H to each of them. So that's what I'm going to do for this. So I'm going to bond my 2 carbons and then split the nitrogens between them, just like that. Alright, so I got to make everybody stable. So N needs 6, C needs 4, C needs 4, N needs 6. So now let me check my total. I'm allowed 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I'm allowed 18. I have 26 valence electrons. Alright, so I have a whole bunch too many. Alright, I have, let's see, 8 too many. 8 extra electrons equals 4 more bonds. Okay, so y'all, the easiest thing I can think to do is I couldn't do like this, because of course then look how many C has. That's not possible. So the way I can split up my 4 bonds is I could do 2 on this side and 2 on this side. So that way my carbons don't have more than an octet. But remember, once you add a bond, you take a pair off of each atom. So I added 2 bonds, so I'm going to remove 2 pairs off each. Here I added 2 bonds, so I removed 2 pairs off of each. So now everybody still has an octet, but I'm allowed 18, and I have 2, 4, 6, 8, 10, 12, 14, 16, 18. Just like that. Alright, so then it says predict the polarity of the compound. Okay, so here's my compound, so I'm just going to answer this one up here. Here's my compound. I know that N is more electronegative than C. So my dipoles are going to go like this. This will be a linear molecule. Notice there's no lone pairs on my central atoms. So those are going to cancel out. So my polarity would be nonpolar. So even though the bond itself might be polar, the molecule is not polar because they cancel out. Alright, so let's erase. See what's coming up next. Oh, well that's it, the end. Alright, so let's y'all, the number one thing that people struggle with on the gas laws chapter is not the gas laws, it's when you start putting them together or combining it with stoichiometry or something like that. So just be careful and just think your way through it. Always look at what you have. If you see a P, a V, number of moles, T, then just think ideal gas law. Even if you realize you're going to need to do stoichiometry or something else, just look at what you have and try to work with it from there.